So welcome to today's lecture. This is another lecture of the course on Cyber-Physical System Fundamentals. Again, I am teaching Embedded Systems Foundations of Cyber-Physical Systems. This is the 11th lecture of the course. This is the third lecture that corresponds to the third chapter of the companion textbook. And again, I will be teaching topics related to embedded system hardware. Today I'd like to remind you of one slide that I did already show during the last lecture, and actually I did already show that in the very first lecture. This is a lecture that tells you that cyber-physical and embedded systems must be efficient. And you should remember that this efficiency comes in a number of flavors. This efficiency comes in the flavor of code size efficiency, runtime, weight, cost, and energy efficiency. And in the context of embedded processing, I'd like to focus on code size, runtime, and energy efficiency. Today I'm starting the lecture by first of all telling you about one trick that we can try to play if we would like to meet these objectives in order to really optimize for these objectives. And that's a trick which is very commonly known and which is used in embedded processing in many cases. This trick is called Very Long Instruction Word Computers, or VLIW computers. With VLIW computers, instructions are included in very long instruction packets. An example can be seen down here, where we have a total of 4 instructions that are placed in so-called instruction slots. And in the instruction packet, in this case, we have a total of 4 instructions, but there may be more. For VLIW computers, one basic assumption is that the instructions included in such a packet are assumed to be executed in parallel. So all these instructions are executed in parallel. They are started in parallel, and usually they are also finishing at the same time. Furthermore, we assume that there is a more or less fixed association of the different instructions or the instruction slots with the functional units that we have in our data path. So like in this case, where one slot is associated with the floating point unit, and 2 of these slots are linked with the integer units, and 1 is linked with the memory unit. Now, in general, this association may be more or less fixed. There are cases where this association is rather tight, where this is really fixed, and there are other cases where there is a little more flexibility. Now, for these VLIW processors or computers, we do already have an advantage in terms of the energy which is consumed, because we only need to provide a single instruction address in order to fetch all these instructions, and therefore in terms of the energy consumption that is required for transmitting the instruction address to the instruction memory, we already have a little bit of saving usually. Furthermore, more savings are feasible because we assume that now the compiler is in charge of generating these parallel instruction packets. Now this means that we are not relying on custom hardware to actually figure out which of these instructions can be executed in parallel, but we leave this to the compiler. So instead of doing that in hardware, like what is done usually in RISC and CISC processors, this is left to the compiler, and this means that usually we are avoiding some of the overhead which is associated with the detection of possible parallelism at runtime. So as a result of that, there were a lot of expectations into these VLIW machines, and therefore many researchers, many companies have tried to really exploit these potential benefits of VLIW machines. However, there is one downside for these VLIW machines. And this is the fact that was a rather strict relationship between these instruction slots and the functional units. It may happen that in many cases we need no operation instructions. Assume, for example, that we have a program where there are no floating point operations. If there are no floating point operations, and if this association between the slot and the floating point unit is very tight, then we might have to use no ops there for such a program. Could also happen that we have quite a number of registers and all the variables can be associated with registers, and that therefore we don't need any access to a memory, so therefore we can also not take advantage of that slot which is there at the right hand side of this little figure. As a result, we might have to place quite a number of no operation instructions into these slots, and this of course means that the instruction density, that the efficiency of the instruction code is decreased. So in order to get around that problem, we can introduce a somewhat more general class of instruction sets, and this more general class is called explicit parallel instruction set computers, or EPICs. With EPICs, we stick to the idea of making the compiler in charge of figuring out what can be executed in parallel, but we are giving up on the constraint that everything that needs to be executed in parallel has to be stored in one instruction package. So what we do in EPICs is then that we try to come up with other ideas on how to encode what needs to be executed in parallel. I'd like to demonstrate this technique with the help of one example using the TMS C6000. For the TMS 3000, we have instruction packets that comprise a total of 8 instructions, and for each of these instructions there is one bit which is reserved, and this one bit indicates whether or not the next instruction in the package should also be executed in parallel. So if it's a 0, it should not be executed in parallel. If it's a 1, the next should be executed in parallel as well. So as a result, in the very first cycle, we will be starting just instruction A because there is a 0 there. And for the second cycle, we will be starting instructions B, C, and D. And this is then the end of the parallel execution there because there is a 0 there. And then in the third cycle, we will be starting the execution of E, F, and G. So in this way, we don't have to encode these no operations anymore. Also, we give up on the idea of having a very strict link between these instruction slots and the corresponding functional units. So therefore, we don't really need to encode these no operation instructions anymore. And we have improved the instruction density in terms of the number of bits that we need for encoding operations. With respect to this architecture, we have still one problem that we have to solve, and that's a problem that with a total of up to 8 instructions per instruction package, we can have quite a number of operations that are assumed to be performed at the same time, which means that we have quite a number of operands to fetch at the same time, which could mean that we would like to provide register files with a very large number of ports. However, we know that memories with an extremely large number of ports are very expensive, they are very large, and therefore we try to avoid them. In the case of the C6 architecture, this is done by partitioning the register file into 2 different register files, into register files A and B, and certain functional units are attached to register file A, and others are attached to register file B, and the compiler is in charge of figuring out which operations can be performed in parallel, and essentially also figuring out which operation can be performed in the so-called data path A and which can be performed in the data path B. So this partitioning is to be done by the compiler. So that's a problem that has to be solved for these architectures that have quite a number of operations performed in parallel. For this C6000 architecture, we still have one restriction, and this is the restriction that parallel execution cannot span several packets. So if we had, say, a very large number of functional units in our architecture, we would possibly like to have 10 or 12 operations to be performed in parallel, and this does not work with the C6000. So therefore, I'm giving up on that restriction as well, and I'm demonstrating that for the IA64 architecture, which is removing that restriction. That IA64 architecture was designed by Intel in cooperation with a number of research institutes. And as a result, there is this proposal to use so-called bundles that can contain up to 3 instructions. And these 3 instructions can be of a number of types. They can be of ALU type, they can be integer instructions, memory instructions, floating point, or branch instructions. And now for the combination of these 3 instruction types, certain combinations are allowed, and these combinations are encoded in a small number of bits, and these bits are encoding the template that we are using for a certain bundle. Certain combinations are feasible. We can, for example, have 1 memory and 2 integer instructions, 2 memory instructions, 1 integer, 1 memory, 1 floating point, and 1 integer instruction, etc. And as a special case, it's feasible to have a 64-bit immediate encoded in 2 of these instruction slots. So for these bundles, we are giving up on the restriction that one such bundle would encode the operations that can be performed in parallel. Rather, we are indicating what can be performed in parallel by defining so-called instruction groups. Now, instruction groups span several bundles. They potentially span several bundles, and they extend up to a position there in our source code string where we have included an underscore. Underscores are delimiting the different groups. So in this case, this means that these 4 operations, 4 instructions will be started in parallel. And then we are starting the next cycle, and then we are going to have 5 instructions that are started in parallel, and over here we have 9 instructions that are assumed to be started in parallel. For the placement of these underscores, for the placement of stops, we have only a limited number of positions, so we can place these stops anywhere in such a string. The essential advantage of this technique is that we can have more parallel operations than could be encoded into any of these bundles. So therefore we have in this way removed this restriction. You might know that the IA64 instruction set architecture is available from Intel. It is available in the form of the so-called Itanium 9300 processor. This processor contains 2 billion transistors. There are a total of 4 cores, and for each of the cores we have an 8-fold hyperthreading, which means that we have a very fast context switch between 8 threads per core. Now, interestingly, the commercial support for this architecture seems to be decreasing, so we will see whether or not that architecture will survive in the long run. I think one of the problems is that maybe for standard PC-like applications it is not really the ideal architecture, but VLIW architectures may be more appropriate for embedded systems. Now, for the VLIW and EPIC architectures, there is one problem that still needs to be addressed. This is the fact that with every clock cycle we are inserting into the pipeline, which also exists for these architectures, quite a number of instructions. So like in this case, we are inserting into the pipeline 4 different instructions, and in this example I'm assuming that one of them is a branch if equal instruction. Now if we execute this a stream of processors, the different instructions will be moved into the pipeline. We will be decoding all these instructions, and we will be starting to execute all these instructions. Whether or not we will take this branch might be decided only at the time when we execute this branch instruction. Now that means that at the time when we know whether or not we have to branch into a certain direction, we do have already spent quite some effort on the instructions that have followed this first instruction packet over here. So all these instructions that you see up here have already entered the pipeline, and some effort has been spent on them, and that also means some energy has been spent on them. Now we could decide to actively ignore all these instructions. However, this would waste some performance, this would waste some compute power, and therefore we try to stay away from that possible decision. Rather, we decide to declare the execution of all these instructions to be a feature rather than a bug. That means that even though this is the conditional branch instruction, and even though we might branch away from this stream of instructions, we declare the execution of all these instructions to be a feature, and the possible slots for all these instructions are called delay slots. The question then is, how do we fill all these delay slots with useful instructions? Because these need to be instructions that need to be executed unconditionally. It's obviously not very easy to fill a large number of delay slots with instructions. Think, for example, of this C6000 architecture, where we have up to 8 slots for instructions per cycle. This obviously means that we have quite a number of such slots. So therefore it's difficult to actually find enough instructions to fill all these slots, and therefore as a general recommendation we should try to avoid branches wherever possible for VLIW architectures. One way of doing that is by using so-called predicated execution. With predicated execution, for each instruction we have one field that is describing actually the operation for that instruction, and in addition we have a limited set of bits which describe one expression that should be evaluated at runtime, and depending on the result of that evaluation we will either actually execute that instruction or effectively turn that instruction into a no-op. This is usually implemented in such a way that the computations are performed, but then this result will decide whether or not the final result is actually stored in the state registers. So with predicated execution we can implement if statements branch free without the need to execute any conditional branch. Now this has a large benefit if we try to implement if statements. As an example, I'd like to demonstrate how we can implement an if statement for the TI C6000 architecture. Let's assume that we have an if statement, and for this if statement we have a condition where I assume that this condition is already available in the registers, and also we have certain computations that need to be performed, and I assume that we have a small number of variables so that all these variables can be allocated to registers. Then For the TI architecture, we can implement this if statement using conditional branches. So this is how it works with conditional branches. First of all, we are executing a predicated unconditional branch, which means that we are branching depending on the value which is encoded there in this predicate field. So if this predicate evaluates to true, we are actually branching to label L1, where we will be performing the two add operations, implementing this set of instructions there, or the set of assignments there. But the branch will not be immediate. We will have some delay, and since there is nothing else to do, we will have to store 5 packets of no-op instructions, which means that that we will be storing a total of 40 slots there for no-op instructions. So if we are not branching, then we have to work on the else part of the if statement. So there we are starting the branch instruction. We will be branching in the end to label L2. And in this case, we are only using 4 delay slots. And then in the 5th one, we are storing these operations that correspond to these 2 assignments over there. This means that in the worst case, we will be needing quite a number of cycles to execute this if statement. This is the first cycle. Then we need another 5, which means in total 6. Another one, in total 7, another 4, this means in total 11, and this is the last one, which means in total, in the worst case, we would be needing 12 cycles. Now with predicated execution, all these instructions can be stored in one instruction packet, and we can execute these 4 statements there as operations that are stored in one instruction packet, and therefore we need only a single cycle. So therefore it's pretty obvious that we can reduce the delay that comes with the execution of if statements. Now the question may be, how far do we actually get in terms of the energy efficiency if we use this trick, if we use VLIW processes? Well, there is one example which clearly demonstrates that it is feasible to design very energy efficient VLIW processes. And this is a processor that has been designed by a company called Silicon Hive, which very recently has been acquired by Intel. And Silicon Hive designed that processor which is able to execute or to start 41 instructions per cycle for so-called software-defined radio. Actually 30 of these operations can be executed per cycle. At the bottom line is that we would be able to execute 24 billion operations per watt, which brings us to about 20% of the energy efficiency of application-specific integrated circuits, which means that we are actually really in this sweet spot of our diagram. And this means that with VLIW processors, we can show that it is feasible to obtain a power efficiency which is close to the power efficiency of ASICs, but still we have flexibility, still we have programmability of the underlying architecture. Now, in the context of embedded processing, I do have to mention other processors as well. A very large number of processors is actually consisting just of so-called microcontrollers, which are very simple processors, and there are some microcontrollers that have been very popular and of which billions and maybe more processors have been fabricated and distributed into different products. A very common example is the so-called C51 architecture, which is an 8-bit CPU optimized for control applications. It does include extensive Boolean processing capabilities. In order to reduce the cost, it comes with a small built-in program memory and built-in data memory. Also, the address space for the program memory and the data memory is rather limited. Down here you see how much memory we would, for example, have included there on a particular chip, and over here we see how much data memory has been included on a particular chip. In order to reduce the cost, this processor comes with a good number of I/O lines which are integrated into the same chip, and also since we are working on real-time applications, it's essential to have timers there included and to have universal asynchronous receivers and transmitters there, to have a good interrupt structure and to have on-chip clock oscillators. And this is actually a very popular CPU that has been integrated into quite a number of products. Now, these different features include those that are really characteristic for embedded and cyber physical systems. You see all these Boolean capabilities there. You see the built-in memory address space. You see the fact that some RAM is included, etc. So that means that this architecture is really optimized for providing low-cost computations in embedded systems. Also, with respect to the different processors that we are using there in embedded systems, I'd like to point to the fact that the use of so-called multi-processor systems on a chip is becoming more and more common. So, for example, there is this trend for processors used in mobile phones to use less and less separate chips, but to integrate as much as possible on a single chip. So, for example, you see over here that the different processors, different accelerators have been made available on a single chip, and only those components that would provide some problems for a digital chip might still be integrated as a separate chip, and this applies to high performance, high power amplifiers, and also to radio frequency and amplifiers that might cause harm to the digital components there on that chip, and therefore in a number of designs these are still left as separate chips. So this concludes the presentation of embedded and cyber physical system processing. And next I'd like to move towards a different target technology.